Did you know helium seems to defy gravity? When you see a balloon straining at its string, reaching for the sky, it's easy to think it's somehow escaped Earth's pull. But science, as always, has a much cooler, more nuanced explanation. It's not magic, it's physics. Helium is one of the most intriguing elements on the periodic table, and its behavior, from birthday parties to the farthest reaches of space, is governed by some truly amazing scientific principles. It's lighter than air, sure, but that's just the beginning of its story. Today we're going to take a deep dive into the world of this incredible element. We'll explore why things float, how gravity plays its part, and what happens when you push helium to its absolute physical limits. We'll even journey into the cosmos to see where it all comes from. It's a story of density, temperature, and the fundamental forces that shape our universe. So get ready to have your mind expanded. Let's uncover some mind-blowing facts about this fascinating element. From the squeaky voices it gives us to its crucial role in scientific research and industry, helium is a true superstar of the elements. It's a noble gas, meaning it's a bit of a loner and doesn't like to react with other elements, but its physical properties are anything but boring. We'll see how it can perform feats that look like they belong in a science fiction movie, all thanks to the predictable, elegant laws of science. Let's get started. Consider the following. So why does a helium balloon float? It's a question many of us have asked since we were kids. The answer isn't that gravity has given up on it. It's all about something called density. Think of it like a boat in the water. A huge, heavy steel ship floats because, when you consider its whole volume, including all the air inside its hull, it's less dense than the water it displaces. The water is pushing up on it with a force called buoyancy that's stronger than the force of gravity pulling the ship down. It's a cosmic pushing match, and the less dense object wins by floating. Now let's apply that to the air around us. The air we breathe is a mixture of gases, mostly nitrogen and oxygen. These are relatively heavy molecules. Helium atoms, on the other hand, are incredibly lightweight. They are the second lightest element in the entire universe. So if you fill a balloon with helium, the balloon and the gas inside it are, as a whole, much less dense than the same volume of air outside the balloon. The surrounding heavier air effectively pushes the lighter helium balloon upward. It's not anti-gravity, it's pro-buoyancy. Imagine a swimming pool, but instead of water, it's filled with the air of our atmosphere. A rock sinks in water because it's denser. A beach ball bobs on the surface because it's less dense. Your helium balloon is like a super-powered beach ball in an ocean of air. Gravity is still pulling on it, but the buoyant force from the air is pushing up with even greater strength. It's a beautiful demonstration of Archimedes' principle. Not in water, but in the very air we walk through every single day. Science is everywhere. Let's be perfectly clear. Gravity is pulling on that helium balloon. Gravity pulls on everything with mass, from the biggest galaxies to the tiniest atoms, and helium atoms are no exception. The force of gravity is universal and relentless. If you were to release a helium balloon in a vacuum, a space with no air, it would fall to the ground just like a rock. Why? Because in a vacuum, there's no air to push it up. There's no buoyant force to counteract gravity's constant pull. This is a crucial point. The reason gravity's effect seems so small on helium is because helium atoms have so little mass. According to Newton's law of universal gravitation, the force of gravity depends on the mass of the objects involved. Since a helium atom is so lightweight, the gravitational force pulling it down is minuscule compared to the force pulling down a heavier molecule like oxygen or nitrogen. It's not that gravity isn't trying, it's just that it doesn't have much to work with when it comes to a single helium atom. So when we see a balloon rise, we're witnessing a battle of forces. Gravity is pulling down, but the collective upward push of billions and billions of heavier air molecules wins the day. Think of it like this. If you and a tiny ant are both being pushed by a gentle breeze, you might barely move, but the ant, with its tiny mass, will be sent tumbling. The breeze is the buoyant force, and you are the heavier air. The balloon is the ant. Gravity is always there, the invisible string pulling on everything, but sometimes other forces can be more powerful. Now let's take helium to a place where things get really, really weird and wonderful, close to absolute zero. Absolute zero, or 0 Kelvin, that's minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit, is the coldest temperature theoretically possible. As you cool helium gas down, it first turns into a liquid, just like water vapor turns into liquid water. But if you keep cooling liquid helium to just a couple of degrees above absolute zero, something extraordinary happens. It transitions into a state of matter called a superfluid. What makes a superfluid so super? Its most famous property is its complete lack of viscosity. Viscosity is essentially a fluid's resistance to flowing. Think of it as fluid friction. Honey has high viscosity. It flows slowly. Water has low viscosity. It flows easily. Superfluid helium has zero viscosity. It can flow without any friction whatsoever. If you were to stir a cup of superfluid helium, it would, in theory, continue to swirl around forever, never slowing down, because there's no internal friction to stop it. This bizarre behavior is a macroscopic display of quantum mechanics. At these incredibly low temperatures, the individual helium atoms lose their individual identities and begin to act as a single, coordinated entity, a sort of superatom. They enter what's called a Bose-Einstein condensate. The quantum weirdness that usually only governs the subatomic world suddenly becomes visible on a scale we can see with our own eyes. It's one of the most striking examples of quantum mechanics manifesting in our everyday world. Well, if your everyday world involves a laboratory capable of reaching near absolute zero, the strangeness of superfluid helium doesn't stop at frictionless flow. Because it has zero viscosity, it can do things that seem to defy logic and gravity in a whole new way. One of the most famous demonstrations is its ability to climb walls. If you place superfluid helium in an open container, you will witness something that looks like magic. A thin film of the fluid, only a few hundred atoms thick, will spontaneously start to creep up the inside walls of the container. It's a stunning sight. This thin film, known as a roll-in film, will continue its journey up and over the lip of the container, flowing down the outside. It's not being pushed or pulled by any external force in the conventional sense. Instead, it's moving due to capillary action and its own unique quantum properties, allowing it to coat any surface it touches and flow to a lower energy state. If the container is open, the helium will literally crawl out and escape, dripping off the bottom until the container is empty. It's the ultimate escape artist. This phenomenon is a direct result of its superfluid nature. A normal liquid would be held in place by its own viscosity and surface tension, but superfluid helium has no such constraints. It can flow through microscopic cracks and pores that would be completely impassable to any other liquid, even a gas. It's a powerful reminder that the universe operates on rules that are often far stranger than we can imagine. And by pushing elements like helium to their limits, we get a peek into the fundamental quantum reality that underpins everything. While helium might seem rare here on Earth, we have a finite supply trapped underground. Out in the cosmos, it's a completely different story. After hydrogen, helium is the second most abundant element in the entire known universe. It makes up about 24% of the total elemental mass of the universe. Think about that. For every 4 atoms out there in the cosmos, roughly one of them is a helium atom. It's everywhere. Most of this helium was created in the first few minutes after the Big Bang. The stars you see in the night sky, including our very own sun, are gigantic factories for creating helium. Stars shine because of a process called nuclear fusion happening in their cores. Under immense pressure and temperature, they take the most abundant element, hydrogen, and smash its atoms together to form helium. This process releases a tremendous amount of energy in the form of light and heat, which is what makes stars shine and what powers life here on Earth. Our sun is converting about 600 million tons of hydrogen into helium every single second. So, helium isn't just for balloons and making your voice sound funny. It's a fundamental building block of the cosmos. It was there at the very beginning, and it's being forged in the heart of every star. Studying the abundance and location of helium in the universe helps astronomers and cosmologists understand the Big Bang, the life cycle of stars, and the evolution of galaxies. It's a cosmic messenger, carrying secrets from the birth of the universe and the fiery hearts of distant suns. It's truly a stellar element. From a simple party balloon to the quantum weirdness of superfluids and the fiery cores of stars, helium is an element of incredible contrasts. It's a perfect example of how even the most familiar things can hold deep scientific wonders. What seems like a simple act of floating is actually a beautiful dance between gravity, density, and buoyancy. What seems like an inert gas can, under the right conditions, become a strange form of matter that flows without friction and climbs walls. It's a testament to the beautiful complexity hidden just beneath the surface of our reality. The story of helium is the story of science itself. It encourages us to ask why, and to not be satisfied with simple answers. Why does it float? Why does it escape its container? Where does it come from? Each question leads us down a path of discovery, revealing the fundamental laws of physics and chemistry that govern not just a single element, but the entire universe. It connects the playroom to the physics lab, and the physics lab to the farthest reaches of the cosmos. That's the power of scientific curiosity. So the next time you hold the string of a soaring balloon, or hear that distinctive squeaky voice, take a moment to appreciate the incredible journey of those tiny atoms. They may have been forged in the Big Bang, or in the heart of a long-dead star, and they are demonstrating profound physical principles right before your very eyes. It's a little piece of the universe showing off its magic. So next time you see a helium balloon, remember, there's a lot more going on than meets the eye.